Indradeep Kumar, Assistant Professor, IARE, Hyderabad. In this video, we will see about the classification of fibers. So our lecture topic will be classification of fibers. So first, what is fibers? So figure 1 shows the periodic table. So this is the periodic table. The conventional metals are shown in yellow color. So these are the conventional metal from which we are getting the fiber, or we can make the fiber. Whereas the materials of the advanced fiber are shown in blue color. So these 4 and 5. So these are the advanced material through which we can make a fiber. Okay. It can be seen that material of the advanced fiber are lighter than the conventional metal. So see, this is above the period, this one, right? In this periodic table you can see, and at the higher level from top to bottom in periodic table, we know that the size of this one and weight is increasing from top to bottom. So here these are above this conventional one. So hence this one definitely it's lighter than the conventional one. These materials occupy higher position as compared to the metals in the periodic table. So here in this periodic table you can see these are having higher position. Thus one can easily deduce that in general these materials have higher specific property, that is property per unit weight, than that of the metal. So these advanced material having higher property compared to the conventional material for getting fiber. So these are only this. So 5 are the advanced and remaining this yellow is the conventional one through which we can make the fiber. Now, properties of fiber. A fiber is characterized geometrically not only by its very high length to diameter ratio, but by its near crystal size diameter. So already we had seen length to diameter ratio should be what? Then we can say that is the fiber, right? That should be greater than 1000. Then we can say that is the fiber. So not only you have to consider, okay, length to diameter is the ratio of length to diameter is very high, then we can say, but about their crystal size diameter also, right? But by its near crystal size diameter. So near crystal size means what? If their diameter is of that crystal size, that we can say that is the fiber. The common structural material, aluminium, titanium, and steel are listed for the purpose of comparison. So just for this one is a comparison for this one. However, a direct comparison between fibers and structural metal is not valid. So let's see here. A direct comparison between fibers and structural metals, this through which we can form the structure, and the fiber we cannot compare, right? That is not valid because fiber must have a surrounding matrix to perform in a structural member. So in a structural metal can be used directly to form a structure, but fiber cannot be used directly. Fiber along with the matrix only can be used as a structural member. So that's why along with the matrix only we can use the fiber, and a structural metal directly we can use. So we cannot compare both. If fiber along with the matrix is there, then we can compare with the structural metal that which one is better. But alone fiber we cannot compare. Where are the structural metals are ready to use, means directly whatever the structural metals are there, without matrix or without anything, directly you can use that one. So now here one note is there. Note that the density of each material is listed because the strength to density and the stiffness to density ratio, or simply you can see the strength to weight ratio and strength to the stiffness to weight ratio are commonly used as indicators of the effectiveness of a fiber. Means by these two we can say that the fiber is effective or not, or how much it's effective. So first, strength to density ratio should be high, and stiffness to density ratio should be high, right? Means it should have greater strength and greater stiffness. Okay, based on that only we can say that fiber is effective or not, especially in weight sensitive applications. So where the weight sensitive application is there, like application of aircraft, space vehicle, where that weight matters a lot, in that case these two things is very important to check whether these things are there or not in that fiber. If these properties are there, means strength to density ratio is higher and stiffness to density ratio is higher, means we can use that fiber in aircraft and space vehicles. If a strength to density ratio is low or a stiffness to density ratio is low, then we cannot use or we will not use in the aerospace or space vehicles. Now see the first time, like boron fiber. The fiber was first introduced by Talley in 1959. So this was introduced by Talley in 1959. In commercial production of boron fibers, the method of chemical vapor deposition is used. So for finding this one, what the method which is used is named as the chemical vapor deposition. Right. So in short, we are telling that CVD is used. The CVD is a process in which one material is deposited on a substrate to produce near theoretical density and a small grain size of the deposited material. So here what happened? One substrate is there, that means one material will be there or one metal will be there. On the surface of that, the other means this new material will grow or will be deposited. Just like suppose one bread is there, and over the bread, what we are doing for making sandwich, we are adding the masalas. So here this masala is the new type of fiber, and here the bread slice is the substrate. Okay, so that grows on the surface of a substrate, so that on which it's a growing, that is called the substrate. Okay, and that should be what near to the theoretical density, whatever theoretical of that material density is there, that should get deposited on that one and having a small grain size for the deposited material. In CVD, the material is deposited on a thin filament. So here just like substrate, so that substrate should be what? Thin filament. The material grows on this substrate and produce a thicker filament. So after what happened, once the material start growing on the substrate and they produce a thicker filament of that one. The size of the final filament is such that it could not be produced by drawing or other conventional method of producing fiber. So whatever the size of filament is there, that should be such that it cannot or it could not be produced by drawing. After that, we cannot use a drawing method or other conventional method for producing the fibers. It is the fine and dense structure of the deposition material which determines the strength and modulus of the fiber. So based on that only, it can be determined the modulus and the strength of the fiber. In the fabrication of boron fiber by CVD, the boron trichloride, that boron trichloride is mixed with hydrogen and boron is deposited according to the reaction. So just here, 2BCl3 G2, sorry here H, gives 2B plus 6HCl. So this one what? In the process, the passage takes place for a couple of minutes. Okay. During this process, the atom diffuse into tungsten core to produce the complete hybridization. So in this case, what happened? Tungsten is diffused to produce the complete boridization. Not hybridization, sorry. It's a boridization, means the process of burning. In the beginning of the tungsten fiber, 12 micrometer is used. This step induces significant residual stresses in the fiber. So in this case, what happens? Significant residual stresses of the fiber is created. The core is subjected to compression and the neighboring boron's mantle is subjected to tension. So neighboring will have the tension. Means the core is experiencing or subjecting compression and the neighboring boron mantles is subjected to tension. Now key features of boron fiber. These are ceramic monofilament fiber. So boron fiber is what? Ceramic and monofilament, means single filament type fiber. Fiber itself is a composite. Circular cross section. So boron having the circular cross section. Fiber diameter ranges between 33 to 400 micrometer and typical diameter is 140 micrometer. Okay, so fiber diameter ranges between 33 to 400 micrometer. Boron is brittle, hence large diameter results in lower flexibility. Thermal coefficient mismatch between boron and tungsten result in the thermal residual stresses during the fabrication cool down to room temperature. So means they can be cooled down at the room temperature. Boron fibers are usually coated with SiC, silica carbide, B4C. So B4C, so that this is a space. B4C means boron. This is B4 C, so that it protects the surface during contact with molten metal when it is used to reinforce light alloy. So when this is used to reinforce light alloy, what happens? Surface with the molten metal state. Further, it avoids the chemical reaction between the molten metal and fiber. Strong in both tension and compression. So boron fiber is strong in both the cases, either tension or compression. Exhibit linear axial strain relationship up to 650 degrees Celsius. Means this can so or this will so that this will obey the Hooke's law, that linear stress strain relationship up to 650 degrees Celsius. After that, only their elasticity will change and then it will move to the plastic region and then it won't obey the Hooke's law. Since this fiber requires a specialized procedure for fabrication, the cost of production is relatively high. So it's relatively high because a special fabrication procedure is required like CVD, hence the cost is higher. Next is carbon fiber. The first carbon fiber of commercial use when was fabricated by Thomas Edison. So Thomas Edison first fabricated the carbon fiber. Sixth lightest element and carbon-carbon covalent bond is the strongest in nature. So carbon is the sixth lightest element in the periodic table and carbon-carbon covalent bond is the strongest in nature. Edison made carbon fiber from bamboo fiber. So Edison made with what? By using bamboo fiber, he made the carbon fiber. Bamboo fiber is made up of cellulose because bamboo is made up of cellulose. So from bamboo fiber is also made up of cellulose. Precursor fiber is carbonized rather than melting. So here in previous what we have seen like boron is melting. So here instead of melting that one, what they are doing, it's a carbonized, means they are allowing to react with the carbons. Filaments are made by controlled pyrolysis. Controlled pyrolysis. So pyrolysis is what? The process in which we are using the heat or heat treatment. So chemical deposition by heat. It's written here. Of a precursor material in fiber form by heat treatment at a temperature of 1000 to 3000 degrees Celsius. At 3000 up to 1000 to 3000, in between that pyrolysis process or that temperature is there at which it's converting to filament. The carbon content in carbon fiber is about 80 to 90%, and in graphite fiber the carbon content is in excess of 99%. So the carbon content in carbon fiber is only up 80 to 90%, but at the same time in graphite fiber the carbon content becomes more and it's approximate even more than 99%. Carbon fiber is produced at about 1300 degrees Celsius while the graphite fiber is produced in excess of 1900 degrees Celsius. So at 1300 degrees Celsius graphite fiber is produced, and at the same time once you will increase the temperature to 1900 degrees Celsius, then it will convert it to graphite fiber. The carbon fiber becomes graphitized by heat treatment at temperature above 18 degrees. So just see here, that's why here it's 1900 degrees Celsius. Why? Because carbon is getting graphitized at 1800 degrees Celsius. So once it's getting more than 1800 degrees Celsius, what happens? Carbon will start graphitizing, and after that whatever the fiber we will get, that is a graphite fiber. Carbon fibers term is used for both carbon fiber and graphite fiber. So directly simply we can use as carbon fiber for both carbon fiber as well as the graphite fiber. The only difference is at what temperature is using. If the temperature is around 1300 degrees Celsius, then we can say that is a graphite carbon, and if same that is heated up to the 1900 degree or 1900 degrees Celsius, then we can say that is a graphite fiber. Different fibers have different morphology, origin, size and shape depending upon how their growth is there. The size of individual filament ranges from 3 to 147 micrometer. Maximum use of temperature of the fiber ranges from 250 degrees Celsius to 2000 degrees Celsius. That's why I just see here at 1900 degrees Celsius only it's getting graphitized. So for converting or getting fiber, that we can heat from 250 to 2000 degrees Celsius. The use temperature of a composite is controlled by the use temperature of the matrix, right? Precursor material, there are two types of precursor material. First one is, so what is this one? First one is polyacrylonitrile, that is called PAN, and second one is rayon pitch. This is the residue of petroleum refining. So after petroleum refining, whatever the residue is there, from there we are getting what? Rayon pitch. So these two are the precursor for getting the carbon fiber. Fiber properties vary with varying temperature. So as temperature will change, carbon property will, that fiber property will also change. Already we had seen if 1300 degrees Celsius is there, then we can say that is as carbon fiber. Now from 1000 to 1800 degrees Celsius is getting graphitized, and at 1900 degrees Celsius we are getting the graphite fiber. So their property vary with the temperature. Fiber diameter ranges from 4 to 10 micrometers. Their diameter ranges 4 to 10 micrometer. A tow consists of about 3000 to 30,000 filaments. So in a tow, there are 3000 to 30,000 filaments of carbon fiber is there. A small diameter results in very flexible fiber and can actually be tied into a knot without breaking the fiber. So that is that much flexible. We can tie a knot, but it won't get break or breaking of the fiber. It's not just like a thread. You can tie a knot, and after that even you can remove that also. So that thread is that much flexible. It's not breaking. But if you try just take one pencil and then try to bend and tie the knot, it's not possible because the flexibility is not that much lesser, means higher. So flexibility higher means even you can tie a knot also. Modulus and strength is controlled by the process. Whatever the modulus and strength is required, according to that can be controlled by the process. The procedure involves the thermal decomposition of the organic precursor under well-controlled condition of temperature and stress. So under controlled condition of temperature and stress, that depending on which type of fiber is required, means up to that much temperature we have to allow only. That means that should be controlled, and how much stress is there, right? With that only you can get that type of carbon, or that is fiber. Cross section of fiber is non-circular. In general, it is kidney bean shape. So carbon fiber is of their shape is kidney bean shape type, not circular. Heterogeneous microstructure consisting of numerous lamellar ribbons. Morphology is very dependent on the manufacturing process. So whatever the morphology will be there, that depends on what? Manufacturing process. Already we had seen that should be controlled manner depending upon how much modulus and strength is required. Pan-based carbon fiber typically have an onion skin appearance. So pan-based carbon fiber, whatever is there, they will have just like onion skin, means layer by layer that is there, with the basal planes in more or less circular arc, means almost that near about the circular arc type. Whereas the morphology of pitch-based fiber is such that the basal planes lie along the radial plane. So in this is a this circular arc, but here basal planes lies along the radial planes only, means along that plane. Thus carbon fiber are an isotropic. What is carbon fiber? Carbon fiber is an isotropic. Now next is glass fiber. Fibers of glass are produced by extruding molten glass at a temperature around 1200 degrees Celsius through holes in a spinneret with diameter of 1 to 2 mm, and then drawing the filaments to produce fiber having diameter usually between 5 to 15 microns. So first what happened, and molten state at 1200 degrees Celsius, glass is extruded by the hole, that is a spinneret, okay, with having diameter 1 to 2 mm. So first with 1 to 2 mm diameter of a spinneret, okay, it's a extruded, and after that whatever the filament is there, that is converting into the fiber filament, or that is fiber having a diameter. So now from 1 to 2 mm it's converted to 5 to 15 micrometer. The fibers have low modulus but significantly higher stiffness. So there is low modulus. That's why even after glass is there, if you will hammer it or just apply a load, that will break. But if you will try to bend, then it can be break. Not it can, means it can, or their stiffness is higher. So you can bend that glass fiber. Individual filaments are small in diameter, isotropic in nature, and very flexible as the diameter is small. Since their diameter is very small, so they are flexible in nature. The glass fiber come in variety of form based on silica, which is combined with other element to create a specialty glass. So just add what? Silica to get whatever the type of glass is required. So what are the different types of glass fiber? Now the types of glass fiber, what are their key features? So these are here. So just see, these red colors are the type of glass fiber, and along with their, it is the key feature of that fiber. The type of glass fiber and their key features are as follows. E-glass, what is feature? Higher strength and high resistivity. S2 glass, higher strength, modulus and stability under extreme temperature and corrosive environment. So in corrosive environment and having higher strength, modulus and stability. R glass, enhanced mechanical properties. So R glass is having better mechanical or improved mechanical properties. C glass, resist corrosion in an acid environment. So in an acid environment also, C glass can resist the corrosion. D glass, having good dielectric properties. Now next is alumina fiber. These are ceramic fabricated by spinning a sludgy mix of alumina particle and additives to form a yarn, which is then subjected to controlled heating. So what happened with ceramic fabricated by again spinning a sludgy mix alumina, so that should be sludgy mix alumina, and additive. Just after adding the additive, what happened? They are forming a yarn, and after forming a yarn, then it's subjected to controlled heating. By that, the alumina fiber can be produced or can be made. Fiber retain strength at high temperature. So at higher temperature also, alumina fiber can sustain or can retain their strength. It also shows good electrical insulation at high temperatures. At higher temperature also, this can be used as a good insulator. It has good wear resistance and high hardness. So wear resistance of alumina is also good and having higher hardness. That's why we are using in the aircraft. The upper continuous use temperature is about 1700 degrees Celsius. So just see up to 1700 degrees Celsius, we can use that one. Fiber of glass, carbon and alumina are supplied in the form of toes. So these are the form of toes. Already we had seen 3000 to 30,000 5 filaments are there in one toes, also called robing or strands. So these are just consisting of many individual continuous fiber filaments. So they are having many continuous fiber filaments. So combination of all the fiber filaments, just we are saying that as toes. DuPont, scientist name is there, has developed a commercial grade alumina fiber known as Alumina FP, that is polycrystalline alumina fiber. So DuPont just developed what? Commercial fiber whose name is Alumina FP. Alumina FP fiber are compatible with both metal and resin matrix. So this fiber can be used with both either metal or resin matrix. Means both type of metal is compatible. So that can be used in both the cases. These fibers have a very high melting point of 2100 degrees Celsius. So this fiber, I've just see the melting point 2100 degrees Celsius. At that temperature only it will melt. So means before that we can use. So that's why here it's given 1700 degrees Celsius is the continuous temperature at what we can use that one. They can withstand temperature up to 1000 degrees Celsius without any loss of strength. So up to 1000 degrees Celsius, there is no loss in strength. Whatever the strength is there, just heat up to 900, 950 degrees Celsius, you can see the same strength will be there. That means up to 1000 degrees Celsius, their strength will be same. After that, if you will heat more than the 1000 degrees Celsius, then their strength starts getting decreases. Okay. They exhibit high compressive strength when they are set in a matrix. So once it's combined with the matrix, then this shows the higher compressive strength. The alumina whiskers are available and they exhibit excellent property. Alumina whiskers in the whiskers form is available and it's showing excellent property. Alumina whiskers can have the tensile strength of 20700 megapascal, or you can say 20.7 gigapascal. That much strength is there, and the tensile modulus is 427 gigapascal. What are the applications of alumina fiber? The alumina has a unique combination of low thermal expansion, high thermal conductivity, and high compressive strength. The combination of these properties gives good thermal shock resistance. Because of this property, they will have good thermal shock resistance. Means even after applying the temperature, higher temperature also, they will sustain their property. Means they will not lose their strength or other property. Even they are showing up to the 1000 degrees Celsius the same. More than once the temperature increases to 1000 degrees Celsius, then only their strength starts getting decreased. So that's why it's their thermal shock resistance. By the change in temperature also, their property won't get affected that much. These properties make alumina suitable for application in furnace used as crucible, tubes and thermocouples. So just because of that one. Why? Because up to 1000 degrees Celsius also that won't decrease, or their strength won't decrease. So that can be used as a furnace and crucible, okay, tubes, thermocouples, sets. The good wear resistance and high hardness property are harnessed in making the components such as ball valves, piston pumps and deep drawings. Because of this high wear resistance and higher hardness, that can be used as a piston pump, ball valves and deep drawing tools. Now next is aromatic fiber. These fibers are from aromatic polyamide, that is nylon family. Right, just like nylon 66, nylon 6 that already you studied in class 12. Aramid is derived from AR, that is aromatic, and amide is polyamide. Means that's a combination of aromatic and polyamide. So that's why after combining this is called as aramide. Means aromatic plus polyamide or amide. Examples of fiber from nylon family, that is polyamide 6, that is that polyamide 6 type. What is that? Nylon 6, and polyamide 66, that is nylon 6. These are organic fiber. Melt a spoon from a liquid solution. DuPont developed these fibers under the trade name Kevlar. So they named DuPont as Kevlar. From polyphenylene terephthalate PPTA polymer. Morphology is what? Readily arranged crystalline sheets resulting into anisotropic properties. So they are just arranging their crystalline sheet type and hence they have anisotropic properties. Filament diameter about 12 micrometer and partially flexible. High tensile strength, intermediate modulus, significantly means in between that modulus is there. Significantly lower strength in compression. So during the compression it's having lower strength. 5 grades of Kevlar with varying engineering property are available. So there are 5 types of Kevlar are there with their different engineering properties. So Kevlar name is, first one is Kevlar 29, second Kevlar 49, then Kevlar 100, Kevlar 119, Kevlar 129. So these are the 5 different types of Kevlar. Now next is silicon carbon fiber, that is SiC. Silicon carbide fibers are ceramic fiber. These fibers are produced in similar fashion as boron fiber are produced. The fibers are produced by 2 methods of follow. So there are 2 methods. First one is CVD on tungsten or carbon core. Already we had seen just like boron type. Okay, here it's either tungsten or carbon, or that both can be used. Means either CVD by using tungsten core or carbon core. And second method is Nickel-on by Nippon Carbon Weapons. That is trademark of that Nippon company. So first one is CVD on tungsten or carbon core. Just like here, that tungsten will be what? That surface over which that will grow. Now this fiber is similar in size and microstructure to boron, and that's why we are using the same method. The fibers are produced on both tungsten and fiber cores. So that can be produced on both the cores. That is only the substrate. These fibers are relatively stiff due to thicker diameter of the fiber. So this diameter are what? Stiff in nature because of thicker diameter. The diameter of the fibers about 140 micrometers. So the diameter is 140 micrometer. The fibers have a strength in the range of 3.4 to 4 gigapascal only. So it's lesser than the boron, and boron having also the lesser diameter. This one having more diameter and hence it's a lesser flexible. Failure strain is in the range of 0.8 to 1%. The Young's modulus is about 430 gigapascal. The fiber shows high structural stability and a strength retention even at temperature 1000 degrees Celsius. So again, silicon carbide also can, their strength can retain up to 1000 degree Celsius also. The CVD with CH3 SiCl3 as the reactant, SiC is deposited on the core as follows. So see here, CH3 SiCl3 in the gaseous form gives what? SiC, that is silicon carbide in solid form, plus 3HCl. Okay, so this will be the reaction. So this is S3HCl, that is the hydrochloric acid in the gaseous form, so that will escape. What happened? Silicon carbide, that is in the solid form, so that will deposited on the surface of the or substrate. The SiC fiber, actually here that this one is there, that dotted, but here it's not showing in this slide, right? Okay, so I'm just putting here. So this is the bullet point. Okay, so actually bullet point I given here, but it's not showing in this one. So I think I just shifted slide more to our left. So okay, so see here. The first, the SiC fiber produced on a tungsten core with a diameter about 12 micrometer. So in case of tungsten, that diameter is 12 micrometer. It shows a thin interfacial layer between the SiC metal and the tungsten core. So in between a thin layer, interfacial layer is there. In case when carbon fiber is used, the fiber diameter of the carbon fiber is around 33 micrometers. So just see, in case of tungsten, the diameter is 12 micrometer. In case of carbon, that's a 33 micrometer. Means this one having the lesser diameter. So when you will produce, or when we will produce on the tungsten core, then that will be more flexible. Both type of SiC fiber have a smoother surface than a boron fiber. So these two both are smoother than the boron fiber. This is because there is a deposition of a small columnar grains as compared to conical nodulus in boron fiber. So in boron fiber, what happens? Their conical nodulus is formed, but here it's a columnar grain as forming. The SiC fibers produced with carbon core and used in light reinforced alloy. These fibers are produced with a surface coating. The composition of this coating varies from carbon rich from inner surface to silicon carbide at the outer surface. So the composition is from what? Carbon rich from inner surface to silicon carbide at the outer surface. So means at the inner surface more carbon will be there, and at the outer surface more silicon will be there. So as you will move from inner to outer side, the carbon content will decrease, or once you will move from outer to inner side, silicon carbide content will decrease. The fibers that are used to reinforce the titanium have a protective layer which varies from a carbon rich to silicon rich, and again to a composition which is rich in carbon at the surface. Okay. Next, the outer surface acts as a protective surface, and when it comes in contact with molten and highly reactive titanium, the fibers are made by a specialty material under the trade name SCS, incorporated under the name SCS6. The coating increases the fiber diameter by 6 micrometers. So already we have seen that is produced as the coating. So because of the coating, the diameter got increased by 6 micrometers. The fiber has low failure stresses due to surface flaw. The higher strength of fiber is due to the control defect at the core metal interface. The strength of silicon carbon fiber produced using CVD is seen to be anisotropic. So that is in isotropic in nature. The radial strength is significantly lower than longitudinal tensile strength. When the fibers are heated to above 800 degrees Celsius in air for a long period, they lose their strength due to oxidation of the carbon-rich outer surface. So since at the outer surface carbon is more, so they are getting oxidized. Hence, their strength decreases. Now the second method, Nickel-on by Nippon Carbon Japan. That is the trademark of Nickel-on. The fiber are manufactured by the process of controlled pyrolysis, chemically deposition by heat of a polymeric precursor. Means again this method also used the pyrolysis, controlled pyrolysis. The fiber is homogeneously composed of ultra-fine beta silicon carbide crystalline and carbon. The filament is similar to carbon fiber in size. So size of this filament also is similar to the carbon fiber. The fiber more flexible due to a smaller diameter. So see, only 14 micrometer diameter is there. So that is smaller, so it's more flexible. The fibers are arranged in tows of 250 to 500 filaments. So this is in the form of 250 to 500 filaments per tow. These fibers come in two grades. The first grade is ceramic grade and second grade is high volume resistive grade. So in ceramic grade, what happens? Ceramic grade provides good high temperature performance and mechanical properties. At higher temperature also their performance is good and mechanical property also is good. And second one is high volume resistivity grade. In that water, it is a low dielectric fiber. It has good electrical and mechanical property, and these are used in dielectric structures. Now, uses of Nicholas trademark fiber. These fibers are used to form fibrous products such as high temperature insulation filter etc. These fibers have high resistance to chemical attack, hence these can be used in harsh environment. So even if the higher resistance is there, right? They are not chemically attacking, they are not reacting chemically. So even in harass environment also that can be used. These are also used as a reinforcement in plastic, ceramic, and metal matrix composite. So this can be used in plastic, ceramics, and all. Now, cross-sectional shape of the fiber. The cross-sectional shape of the fiber of various types we have studied above are different. Means already it's not circular for all the cases, having different shape. The cross-sectional shape of the fiber, although is assumed to be circular, is not circular in general. But generally we are considering circular, but exactly it's not circular. The various cross-sectional shape of the fiber are shown in figure. So for circular, this one of fiber name is glass, carbon, organic fiber, alumina, silicon carbide. Elliptical, that diameter is elliptical. Okay, our cross-section area is elliptical for alumina and mullite. Triangular for silk, silicon, carbon, carbide viscose. Hexagonal is for sapphire, that is Al2O3 viscose. Rounded, triangular, that is sapphire, Al2 or single crystal fiber. Kidney wheels, that for carbon, that already we had seen. Trilobal, so just 3 lobes are there, so that's why it's named trilobal, that is for carbon and rayon. Now, fiber property. The following are the important points regarding the fiber properties. What? Density, axial modulus, axial Poisson's ratio, axial tensile strength, and coefficient of thermal expansion are some of the important properties. So these are the important properties. Advanced fiber exhibit a broad range of properties. So if advanced fiber is there, they will have even more than these properties. Properties of carbon fiber can vary significantly depending upon fabrication process. So how it's manufactured, or based on that their properties will be there. Just like we had seen carbon at 1300 degrees Celsius, it's a carbon fiber, and at 1900 degrees Celsius, it's a graphite fiber. So once temperature will change, their property will change. For the advanced fibers studied above, one can attain higher modulus. So they have higher modulus even greater than 700 gigapascal, or high strength that is greater than 5 gigapascal, but not both attainable simultaneously. This for the advanced fiber that can be achieved, that modulus can be achieved as high as even more than 700 gigapascal, and strength also greater than 5 gigapascal, but not simultaneously. Either modulus will be higher, then strength will be lower. If strength lower you want, then the modulus will be lower. This both cannot be attained simultaneously. As the 6 IM8 boron and sapphire fibers offer the best combination of stiffness and strength, but have large diameter and thus limited flexibility. Because of the large diameter, they have limited flexibility. However, IM8 fibers are exception for flexibility. The specific stiffness of some of these fibers is almost 13 times of a structural metal. Whatever the structural metal is there, like iron, copper, and all, their stiffness, for this case carbon fiber, 13 times more a structural stiffness. Similarly, the specific strength of some of these fibers is almost 16 times of the structure. So the stiffness is 16 times from the structural metals. Weight saving when the composite of these fibers are used is tremendous due to high specific stiffness and strength. So the C is 13 times and 16 times. Their a specific stiffness and strength is there. So now actual property of composite, that is fiber plus matrix, are reduced. Once we combine with the fiber and matrix, their property is getting reduced. A specific property are reduced even further when the loading is in a direction other than the length direction of the fiber. So instead of like fiber is there, okay, instead of in this direction, loading is there. If loading is like this, right, then their property also will change. Tolerable property means this property can be changed or can be this one. One can get the desired heat transfer or electrical conductivity with proper designing. So with proper designing, we can get the desired heat transfer with that also. The increased fatigue resistance is attainable with the use of these fiber composites. So if where the fatigue resistance is higher, but more required, we can use this carbon fiber to form the composite. Aging effect can be significantly lower. So by using this, the age of the fiber or that composite can be increased also. Means with the time they won't get damaged or wear and tear will be there. Note: the fibers are classified based on their value of modulus as follows. So if modulus based on the modulus only, so ultra high modulus, that is named as UHM, modulus should be greater than 450 gigapascal. High modulus, that is named as HM, their modulus will be between 350 to 450 gigapascal. Intermediate modulus type, that is IM, modulus between 200 to 350 gigapascal. Low modulus and high tensile type HT, that is modulus less than 100 gigapascal, that tensile. So this is the reference where you can refer for these things. Okay. So if you have any doubt related to this video or anything, you can just comment on the video. I will answer that one, or you can just contact me regarding your doubts. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.